Hi, class. So, probability is regularly applied in the medical sciences for decision making and specifically associated with identifying how good a medical test is or if someone has a certain disease. So, let's take a look at some of the terms that are used in these medical fields and how the probability is applied. Sensitivity is the test's ability to give a positive test result when a person who was tested actually has the disease. So that is the probability of getting a positive test result given the person is disease positive or has the disease. Specificity is a test's ability to give a negative test result when the person who was tested does not have the disease. So that is the probability of a negative test given that the person does not have the disease. Then we have something called positive predictive value. Positive predictive value, also known as PPV. That's the proportion of true positives among the positive test results. So it's the percent of people who have the disease that tested positive. So it's the probability of having the disease if you receive a positive test result. And then we have the opposite of that, which is going to be a negative predictive value, which is NPV. And it's the proportion of true negatives among the negative test results, or the percent of people who do not have the disease given that they tested negative. So it is the probability of no disease given that they had negative test results. Let's look at an example. Colon cancer, which was historically a disease for older people, is a growing concern due to rising incident rates in younger adults. These results come from a clinical trial of 2,500 people under the age of 50. So you see we have either positive or negative test results, and the person either has colon cancer or does not. And 32 people were positive and had colon cancer, 3 were negative and had colon cancer, 35 had colon cancer total, and so forth and so on. So we are going to calculate various probabilities that someone in a medical profession might want to know. So the probability of having colon cancer here is just the number of people who had cancer, which is 35 over the total people, which is 2,500. And that is approximately 0.014. The probability of not having cancer is the number of people who did not have colon cancer. That was 2,465 over 2,500, which is 0.986, or about 99% of the people didn't have cancer. Then we're asked to calculate sensitivity. Sensitivity is the probability of having a positive test result given that the person has cancer. And remember, for probability rules, that means we have the probability of having a positive test result and the person has cancer divided by the probability of the person having cancer. So the number of people who have a positive test result and cancer are 32 out of 2,500. The number of people who have cancer total is this whole row, so it's 35 out of 2,500, and that's 32 over 35, which is 0.914. And now let me clear up my contingency table circles. A false negative is the probability of getting a negative test given that the person has cancer. So we do the exact same thing we just did with sensitivity, but with the appropriate number. So it's the probability of having a negative test and cancer divided by the probability of having cancer. Well, the negative test results who had cancer, there were 3 of those out of 2,500, over the number of people who had cancer was 35 out of 2,500. So that's 3 out of 2,500. And that is 0.086. So about 9% of people got a negative test result even though they had cancer. Then the false positive rate is the proportion of people who got a positive test result but did not have cancer. So again, same math here, you guys. Probability of having a positive test result and having no cancer. Whoops, let me rewrite that. Positive test result and no cancer. But this time we're dividing by no cancer. Probability of no cancer. So positive test result and no cancer is 320 people. So that's 320 over 2,500. And the number of people who had no cancer was 2,465 total. 2,465 over 2,500. And that's 320 over 2,500, which is 0.130. Specificity then is the exact opposite of that. It's the test result's ability to test negative when the person doesn't have cancer. So that is the probability of negative test result and no cancer divided by the probability of having no cancer. And so we're looking for this one's specificity, negative test result. Given that the person has no cancer, there's 2,145 of those over 2,500. And the probability of not having cancer is just 2,465 over 2,500. So that's 2,145 over 2,465, which was 0.870. And of course, we could have used the complement with each of these two, and each of these two, and each of these two, because once you calculate one, the other one's just 1 minus the first one you calculate. All right, so the next thing we're going to do is the positive predictive value. Positive predictive value is the chance of having cancer given that you got a test result. So you kind of assume that if you got a positive test result, your risk of cancer is very, very high, right? Well, probability of cancer and positive test divided by the probability of a positive test is equal to, well, let's look up cancer and positive test. Colon cancer and positive test, there are 32 of those. So 32 over 2,500. And then the probability of a positive test result, there are 352 of those. So that's 352 over 2,500. So positive predictive value is 32 over 352, which is 0.091. So if you get a positive test result, you still only have only 9% of those people have cancer. So your chance of having cancer or thinking you have cancer is much lower than it actually is. All right, and the negative predictive value is the probability of no cancer given a negative test result. So probability of no cancer and negative test divided by the probability of negative test. So no cancer and negative test, I'm going to look at the contingency table. No cancer and negative test is 2,145 over 2,500 divided by negative test is 20, nope, let me look. negative test. Yep, it's 2148. 2148 over 2500. And that is, oops, dropped my pen. 2145 over 2148. And when you do that math, you get 0.999. Notice that the positive predictive value and the negative predictive value are not complements of each other. However, probability of cancer and no cancer are complements. Probability of sensitivity and false negative are complements. False positive and specificity are complements. So there's some relationship there. We wouldn't have had to do all of these probabilities. We could have used the complement if we recognize those things. All right, so why did we just do all of this? Because of something called Bayes' rule. The generalization for the positive predictive value or negative predictive value, which is what most medical professionals actually want, is actually an application of a probability rule called Bayes' theorem. That is, the probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of A times the probability of B given A plus the probability of not A times the probability of B given not A. And for our example, in calculating PPV, event A has cancer and event B is a positive test result. Well, the Bayes theorem application is the probability that the person has cancer given that they got a positive test result. So that's the probability of having cancer, which is 0.014 from our math. Probability of having a positive test result given that they had cancer is 0.914. And then that's going to be in the denominator too. Plus the probability of having no cancer is 0.986, and probability of having a positive test result given no cancer is 0.130. And I just pulled these numbers from all of our test results above in our probability math. So I'm going to do this one here. It's 0.014 times 0.914 in the numerator divided by all of 0.014 times 0.914 plus 0.986 times 0.130. Remember, if you're putting this into your calculator, the numerator either has to go in parentheses or you have to do the numerator and hit equals. And then the denominator will have to be in parentheses because there's a plus down there. Put all that in your calculator and you get 0.091, which is what we got up here when we had the raw numbers. But sometimes you don't have raw numbers. You're given sensitivity and specificity of a test in percent form, and so you have to use Bayes' theorem to apply this. That's what you're going to see in your practice assignment. Bye, everybody.